For the introduction, I'm Yao Qianling, a PhD student from Chinese Academy of Science. I'm here to present our paper, Generating API Specification for Bug Detection via Specification Propagation Analysis. So first, as we know, API. As we know, API are common and essential in software development. As this API can cause various effects, developers should follow their API specification. Like the example here, after a successful call to the get device, developers should release the reference come with the put device. The bug violates this and cause the bug. An API specification plays a key role in detecting such bugs, as without them, we cannot detect the related bug. Previous work has proposed various methods to extract specification, which rely on different API artifacts, such as API document, frequent API usage, and bug patches. However, these methods depend entirely on the available API artifact, and their effectiveness is limited. For example, if an specification is not documented, it's impossible for document-based method to get this. And in fact, many specifications are hidden and cannot be observed through internal artifacts, and without them, we cannot detect the bugs. To address this, our research explores if we can infer hidden specifications from the observable ones for better bug detection. So first, we represent API specification using a triplet focused on API post handling. This type accounts for over 16% of API misuse cases in C language. So each specification consists of target API, critical variable, and post operation. It indicates that after a target API call, developers should perform the post operation on the critical variable. For example, for the specification related to the bug here, the target API is get device, which requires a reference to the device, and the critical variable is def. This is also the first argument of the target API get device, and the post operation is put device, which releases the reference count obtained from the get device. We can use such a specification for bug detection to check if each target API is followed by a corresponding post operation. Also, path conditions are considered in bug detection, but they are not the focus here. So, in this work, we observe that API specification can propagate through the API call chain, as API are often designed in a hierarchical manner. When up-level APIs calls lower-level ones, it may inherit the specification from the lower-level APIs. For example, the bus file device called get device, and the specification tied to get device propagate to the bus file device. This means after calling back file device, it also needs a corresponding put device. We then define the specification propagating, and there are three conditions that must be met. So first, the success API must call the predecessor API. Here, bus file device calls get device, which introduces the effect on the critical variable. And second, the critical variable must be propagated to the success API, either as a return value or an argument. Here, def is the return value of the bus file device. And second, there are no intermediate operation disrupt the propagation. So here, between the call to the get device and the return of the bus file device, no other operation affects the critical variable. Therefore, the specification propagates. So by using no specification as a sys and perform propagating analysis, we can uncover hidden API specification for better bug detection. Therefore, in this paper, we introduce API spec chain, which generates new specification from sys. It has two steps: specification propagating analysis and specification generation. The first step identifies which API that the C specification may propagate to or come from. This involves the caller and callee analysis for the C API. And the second step generates specification for the infer API. This means determine their corresponding post-operation. Here is the example of generated specification and the detect bug. The left shows the generated specification for the two functions. So starting with the get device specification, API spec-gen perform propagating analysis and identify the classified device inherit the specification. And similarly, the NFC get device inherit from classified device. API spec-gen further infer that NFC put device is the post operation for the NFC get device. And use the generated specification, we detect a new bug as shown on the left in the Linux kernel. And the code here, after calling the NFC get device, the code used def but didn't call the NFC put device to release the reference, leading to a reference count, and this bug also has been confirmed and fixed. So next, we introduce some technical details. In the propagating analysis, API spec-gen perform caller analysis to identify successor. For example, if the C API is the get device, first API spec-gen gets its caller, including the four functions as shown here. They are the potential successor for the Cs. And second, for each caller, API spec-gen check whether the critical variable is propagated to the caller and the function don't meet this condition are fleet. And next, API spec-gen further check if the specification, if any operation affect the specification propagate, and the function that doesn't meet this condition are also excluded. And finally, API spec-gen identify only the bug-fied device and the classified device are the successor of the specification. So, and then through the interreactive propagating analysis, API spec-gen further identify that NFC get device inherit its specification from the classified device. And next, API spec-gen then generates specification for these APIs. Because the post-operation may be changed during the propagation, we propose to combine API usage and data flow validation to determine the post-operation. API usage help to identify candidates for the post-operation, and the data flow validation help to determine the correct one. For example, the post-operation for the get device is put device here, and this remains the same for the classified device API, but for NFC get device, the post-operation changes. So to determine the correct post-operation, we first analyze API usage and collect operation after the critical variable. After NFC get device, and in this case, the candidates for post-operation are shown here. And second, API spec-gen validate each candidate against the C post-operation. And here, the NFC put device passed the critical variable to the C post-operation put device. Therefore, it was determined as the post-operation for the NFC get device. And finally, we generate the specification shown on the bottom right. They are further used for bug detection. And so in evaluation, we evaluate API spec-gen in Linux kernel using CSC specification obtained from the bug patches. They are covering specification about reference count, memory management, and error check. We evaluate API spec-gen effectiveness on the specification generation, bug detection, compare them with SOTA methods. We also evaluate the ability of the API artifact, such as document. Result shows that API spec-gen generate a total of 7332 specification from just 6 seeds. This process took only 2 hours, averaging 1 second per specification. And a manual check on a random sample confirmed these specifications are correct. And using them, we detect 186 new bugs in Linux kernel, mainly due to improper postal handling. for the target API, and most of them has been confirmed. And we evaluate sort methods for specification extraction and bug detection. This method relies on different API artifacts, including API document, bug patches, and frequent API usage. And results show that sort methods fail to extract most of the generated specification and fail to detect the corresponding bugs. And over 18% of the generated specification are not mentioned in the API document, and over 19% are not frequently followed in the code. Therefore, the sort methods are limited by the API artifact, thus fail to extract the specification. From the results, we also find the inverse API can be very different from the C API, as shown here. And also, API specification is effective across different programmers, including OpenSSL and FMP. In summary, API specifications are crucial for detecting API bugs. Previous work often rely on API artifacts to extract specification, but their effectiveness is limited. And in our work, we introduced the idea of API specification propagation, and we designed the free-world API spec-gen to generate specification using Cs. And evaluation shows that it's effective and can generate thousands of specifications from just few Cs. And importantly, most of them are not documented and benefit from the generated specification. We also detect 186 new bugs in Linux kernel. And API spec-gen is also open source and has passed the artifact evaluation. And you can have a try. That's all. Thank you.
Okay, so I'll start off with a question. So I can't help but think that a lot of the times these bugs are due to the fact that C code doesn't have certain language constructs. For instance, in Python, you have a try finally block. Where I don't know if you're familiar with Python, but you can. It's very idiomatic in Python. You either use with as a specifier, or you have a try finally block where you know that the finally will always get executed to release a law or do some other action. But I also noticed that some of your bugs were that you detected were things where there was some higher level function or some recursive function that had acquired some resource that then things weren't released out of. Do you have any sense for how often a tool like this would work on a language like Python that has these more advanced features? Do you think you'd find a lot of bugs there, or do you feel that the change in language would make a big difference?
In fact, yes, many bugs here may related to the C language that doesn't have many proper resource management, and for other language, Python things will be different. And I guess that may be much effective in another language like Python.
Okay. And I'll take the opportunity to ask one more question. You use this on memory-related issues inside of the kernel. Do you think that this tool would also be an effective tool for finding bugs inside of Apache, Nginx, other kind of user space programs that are not kernel code?
Yes, it's also effective on other programmers because the idea base behind is the API specification propagate. Because API designed in a hierarchical manner, this design also works on user space programmer. We only test it on OpenSSL and FL and PAC for the generation. We didn't have a try for finding bugs, but I guess it would also work.
Okay, I think that'd be very interesting future work. Awesome.
Yes.
All right. We have another.
Thank you for your presentation. My question is related to you talked about some of the functions that did not have names that were related to what they were doing. I don't know if you remember that.
Sorry.
So you mentioned in your slide that there were some functions, some API calls, of which the names were not related to what they were doing. I think I've seen that somewhere. Can you go back?
In the evaluation that we, you mean here?
I think, yes, this on the bottom.
Yes, here, because here is because for some resource-related API, it often have a subroutine line new request allocate some kind of subroutine to indicate he allocating some resources. But we often also find some API allocating resources, but we cannot get this information from their name.
Okay, so my question would be, how did you find out what the functions were doing, given that that context was not there?
Yes, because it's based on our work. We perform propagating analysis. We do not rely on the API names. In fact, we inspect how the critical variable and the specification propagating through the call chain. Even though, depending on the API name, thus we can find this specification.
Okay. Do you think that's a way to maybe comment code that has not been commented yet? I mean, I'm just thinking out loud. So like if you are able to identify the specifications, even if that context is missing, can you backtrack and then explain what a function does based on like those specifications?
We do perform some analysis on why this API name do not contain some informative subroutine, and find because they are very high level and contain very complex semantic. Therefore, their name tend to express their other functionality semantic and ignore some other semantic.
Okay, thank you.
Awesome, great question. All right, thank the speakers again.